Now, why did I say that there's an uncertainty in Garen's car's position? We said about 3 feet, and that's because if we were to look at this table, the table has certain dimensions. The car is not exactly the same size as this table, right? So let's say that this is the dimensions of the parking spot. The car, the center of the location of the car, let's say one day Garen parks more towards the left side. One day he parks more towards the right side. So there's an uncertainty of some number here. One day he parks deeper into the spot. One day he's more shallow into the spot. So there's an uncertainty. So maybe there's a 4-foot uncertainty along this direction and maybe a 2.5-foot uncertainty in this direction of where he parked his car. So you can see that there is a delta x, delta y uncertainty with Garen's position as well. And here I said 3 feet. Now what quantum mechanics says is the product of the uncertainty of position multiplied by the product of uncertainty of the momentum is greater than some number. Typically h cross just is the same as saying h, Planck's constant, divided by 2 pi. Right? So Planck's constant divided by 2 pi, the product of the uncertainties is greater than this. So quantum mechanics says that at a very fundamental level, you cannot state, if you know the precise position of a particle precisely, infinitely precisely, then its momentum is infinitely open. Right? But in real life, we cannot, so that's why you can never say that a particle, a quantum mechanical particle, is absolutely stationary. It always is. It's somewhere there. I don't know where exactly. It's like Garen's car. It's somewhere. We can reduce the uncertainty, but we can never take the uncertainty down to 0. So that's what the uncertainty principle is about, right? So there are 2 manifestations of the uncertainty principle that are common. The first one is this delta p multiplied by delta x is greater than a constant. The second manifestation is the uncertainty, the energy, delta E multiplied by the uncertainty, the time, is greater than or equal to h over 2 pi. So again, that's another kind of uncertainty. The uncertainty of the energy of the particle multiplied by the uncertainty in the time coordinate of the particle is greater than a constant, right? So it's interesting that from a philosophical perspective, this uncertainty is what opens the door to make our universe not deterministic. If our universe were completely deterministic, like a Newtonian universe, like a clock winding down, there's no possibility of free will, no possibility of consciousness, right? No possibility of any of the things that we associate with humans and life. What opens the door in our universe for the possibility of free will, the possibility of consciousness and all these kinds of things, the possibility of mind, is the uncertainty principle, right? And of course, there are people who are arguing that these things are all illusions, which seems to me, they're arguing there's no such thing as free will, they're arguing there's no such thing as mind or consciousness, which seems to me an exercise in shooting yourself in the foot. I have to exercise my free will to argue that I don't have free will. I have to exercise my consciousness to argue that I don't have consciousness. I have to exercise my mind to argue that I have no mind. Right? Which, yeah. So that's the uncertainty principle. Now, here's an application of this, of a quantum mechanical device. Photodetectors. Any of you who use, you've got a garage door at your house, right? You press a little button and the garage door goes up or comes down. Let's say that the garage, you press the button that says garage door, please do come down, right? Garage door comes down part of the way and decides no and goes back up. What happened?
Something done laser.
Yep. So you probably know that on either side of your door, on one side is a LED or a laser emitting source, the other one is a receiver, right? And what happens is, if the beam travels, if the laser beam or whatever beam travels from the light beam travels from the emitter to the receiver, a signal is sent to the garage door saying there's nothing obstructing the path of the door, so it's okay to shut the door. Then when you press the button, the door shuts. However, if there's something obstructing the path, like a kid, right, or your car, you forgot to pull your car in all the way, then what happens is that beam is interrupted, so it does not send a signal to the unit, the control unit. So no matter how much you press the button, the garage door says, no, I'm not going down because there's something in the way. I don't know what it is, but something, right? So that's an application that you probably all experienced. Here's another application of a photo gate. What's called a photo gate is basically where you have a light source like a flashlight, and here's a receiver, right, metal. When the light is on this, it creates a voltage. Now, what happens is, you got a photo gate here. You throw a baseball or shoot a gun, right? So you got a bullet or a baseball traveling here, and what happens is, as soon as the bullet or the baseball cuts this light, right, it obscures the path of this light, what happens is you end up with a dip in the voltage, right? Measured here. Then the bullet or the baseball travels on, and the voltage comes back to normal. Then as soon as it hits here, what happens is there's a dip in the voltage here. So you end up with a dip from the voltage here, and some period of time later, 0.776 seconds later, there's a dip in the voltage here. Now you know the distance between here and here, and you're able to figure out the time difference between there and there because you can use the electronics to tell you exactly how many seconds. And you've got the time, you've got the distance, and you can calculate the speed. So this is how you can travel. You can calculate the speed of a bullet, for instance. I mean, it's hard for most of us, unless you're in the Matrix or something. If somebody shoots at you, to see the bullet coming by and saying, oh yeah, it took 3.7 seconds to travel from here to there, right? So these things are traveling so fast that in real life you'd have to use a setup like this to measure the speed of the object, right? Interestingly, I came across the reference, I think one of the students may have mentioned it to me as well, that I saw a headline somewhere on some science site that mentioned that they've come, like some university, they've come up with a time-lapse photography that's so fast that they're able to capture the speed of a photon traveling. Sounded really weird, right? And I'm a bit skeptical, at least of my understanding as stated, right? But what happens is the time lapse is so fast that you're able to see the object traveling at very, very high speed. Okay, so just a reminder for you to go ahead and do the multiple choice questions on these.